I mean, you hand in the old value into the computation, and then you do something that can involve the state, and you return not only the result of the computation, but an updated value of the state. So in this, I mean, the interesting case in this sense is this first one with the leaf. So the old state is this next label, and we use it to label the leaf, but then we update the state by returning next label plus 1. But I mean, we don't really in place update something. I mean, we hand in the old state and return the new state as part of the result. So that's the idea, how you can do like stateful stuff in Haskell without actually changing something, but passing through the current value of the state and then updating it. And we can define a type synonym for that. We can call it state SA. So that's the idea is it's a stateful computation where the state type is S and the result type is A. So what I just said is we hand in the current value of the state and we return an updated value of the state and the result. Okay, so that we can do. And now let's look at this part here for the node. So what did I do? I mean, the old state was next label. So then I have this stateful computation label prime applied to the left child, and I get the result, the labeled left child, but also an updated state. And now I need the second stateful computation to do the right child as well. Now I have to be careful and concentrate that I, for the next stateful computation, because now the first computation changed the state from next label to new next label. So now when I do my second computation, I must use this updated state, new next label. And it can again be changed, and I get an even newer next label. And so I mean, often people say they thread the state through the computation. So if you have two in this case, you start with an old state, then the first computation may update the state, and then you have to pass this updated state to the second computation, which may again update it. And first of all, that's a bit annoying to write, and secondly, you can also make a mistake. I mean, for example, I could have, instead of new next label, I could have used next label here, and then it would go wrong. And therefore, we can automate that, because that, I mean, you only have seen one example now, but I mean, yeah. And I mean, of course, I call it bind state. So we have a stateful computation and a way to continue with the result of the first stateful computation. And we can combine the two to a stateful computation. So I have my S and a way to continue. So what do? I now do exactly the same as I did for the example we have with the left and right child. So, or let's call it, I don't know. No, let's not call it anything. Right. So I mean, the result state is just a synonym for a function. So it's, maybe, I mean, maybe it's clearer if I do this. So or initial state or old state. So I start with, I mean, I must produce a function. State SB is just a function. So I must say, for a given current state, what should that be? So I start with an old state. Now I can apply this stateful computation to the old state. And I get a updated state and the result of the first computation. And what? Oh yeah, it's lambda, yes. And now I can take this updated state and feed it into the new. So now that I have the result, I can apply k to it to get another stateful computation. So ka, and now the state has changed. So instead of the old state, it gets the updated state. and this is whatever I call it, final state or newest state, and a B. And this is actually what I don't even have to call it anything, because that's what I return. So I can whatever. I think I leave it like this. Yeah. Right, so this is the idea. I have two stateful computations. I make my state explicit by not using a mutable variable, but instead always like handing the current value around. So each stateful computation receives the old value of the state, the current value of the state, and produces a result, but also the updated value of the state. And if I now have two such beasts, then what I need to do is, as we saw here, I apply the first computation to the current state. I get an updated state, and then I apply the second computation to the updated state to get the final state. And this is exactly what I've written here. And now with this, okay, that's one thing. And then there are two other things I can do to make this more explicit. I can define a get to get the current state. So that's a stateful computation returning in S. I mean, it's just a way to get to the current state. So it's a function that takes the current state. So just looking at the state doesn't change it. So the new state is the old state. And the result of this is just a state. So it's a way for me to look up the state. And that looks silly, but it will look very nice soon. So like dually, we have a put, so to update the state explicitly. So given a new value for the state, I can do a stateful computation that doesn't have an interesting result. So put new state is the function that takes old state to, well, the new state is the new state, and the result is just unit. Okay, and with those three things, let's try to write this tree labeling much nicer. This label prime. So let's call it, I don't know, label S for state. So it's a stateful computation. The type of state is int. And, it takes a tree, of course, as input, the tree. And it's a stateful computation that results in a tree, okay. So this is just exactly the same signature as before. I just plugged in the state definition. And I think I swapped around the tree and the original state. So I should have done this here as well. Would have been better to, maybe let me do this. So I should have written int here. I mean, just swap the two arguments. And then, of course, I must do this here as well. So the next label comes here. And then, of course, this doesn't work anymore. So it's now second of label prime T1. Right. Okay. It's just nicer because now you see, because we learned that the function arrow is right associative, that this here is exactly state int tree int A. So the signature here is exactly the same as before. And now I can use these new things. So what do I do in the leaf case? I look up my current state. First of all, okay. I mean, this next label is now not explicit anymore. So let's first worry about the leaf. So what do I do in this case? I look up the current state. I increment it by 1, and I set the new state to 1 higher. And then I return, I'm done with, and that I actually should also do. Sorry, one more thing. I mean, if I'm done, if I want to return a value, let's call it pure S, or just, yeah, pure S. So given a, so this is a stateful computation that doesn't need the state. It doesn't have to look at it and doesn't change it. So if I have a stateful compute and just returns the A. So that's the function that takes the current state, doesn't mess with it, so it keeps it and just returns the given A. Okay, and now with this get, put, and pure, and this bind state, I can finally write this much nicer. So what do I do in the leaf case? Or what would you do if you did that in JavaScript? You would look up the current value of next label, then you would increment it by 1. I mean, update it to +1, and you would return with the leaf where you use the current label as the label. And we can now, and that's 3 steps. And now we have now special functions, get, put, and pure, to do all these things, and we have our bind state to like chain computations together. So now we can write this like much more imperative as follows. We can say first we get the current value, and we bind this with state, and we call the result of getting it, I mean, what did we call it before? Next label. And now again, probably this bite me.
The signature, we bind this in the signature. It's wrong.
What the bind? I'm sorry?
No, the bind is the last function signature has an extra parenthesis there. The level S signature.
Yes.
Has an extra parenthesis in the last 3.
Oh, yeah. This. Okay. So I look up the current state. I update the state with next label +1. This didn't have an interesting result, so I don't care what the result of this is. I mean, it's unit, I could write unit. And now I just don't mess with the state anymore and just return the leaf, which has this next label as label and the old value. And now I get, why do I get?
It keeps going forever.
Let me just briefly comment that, whether this part is correct. Yeah, looks good. Yeah, now it's yellow because of the case distinction. Okay, so using these new things, the get, the put, the pure, and the bind state, I can now write that. I mean, it looks more or less, if you squint, like you would write it in JavaScript. I mean, you look up the value of next label, you update the value of next label by incrementing it by 1, and you then, without messing with the state, it's not lead, it's leave, you return the pair next label and the original value of the leaf. So in the case of this G, it would then be 1G. Okay, and in the leaf case, in the node case, this is simpler actually now. So if we have label as node left right, so we just do the left thing and we do the right thing. So the result of this is, label as the left child. The result is the newly labeled left child. And we do the right child. The result is the newly labeled right. And now we don't have to mess with the state anymore. And we just return the labeled children. Okay, and this is that. And this is certainly I mean, much simpler as before. And I mean, in order to try it, I could define.
Yeah, switch the position of next level L.
Right. Because I changed the parameter position. Sorry. But the rest is still working. Okay. No, now I could have a function like this, but I also don't need to. I mean, I could define one of this. I mean, I could redefine that to use label S instead, but maybe I don't even bother. I mean, it's also nice to see that in action. If it then was correct, of course.
You have to save.
I have to save. Right, I don't need this.
No, there. Yes, in the put.
In the put. Sorry, yeah. I don't need this here because I just overwrite the old state. So I could say const. Anyway. Okay, now let's try this. So let's use our label S now, and it takes the tree and it takes the first label. So let's say 1 again. And now it returns the 4 is now the next label. So after I've labeled those 3, the next label would be 4. And it returns the tree again, I mean, with the labels as before. So it works. And now, I mean, if you just squint at the implementation, I think it's very nice. Now, it's very close to what you would have done in JavaScript. If your state was a mutable variable. In the leaf case, you look it up, increment it, return the leaf with this label you just looked up. And in the node case, you just first label the left here and then label the right tree. Right. And I think we should have a break now. And then, yeah? Okay. Yes. I mean, it's 1.5 hours or something almost. Yeah. Yes. And then, so that's that. So we have now seen 3 examples, maybe, either, and state. And we have seen I/O on Friday, and now we have these funny bind functions now, and then we'll look at them and see that they have similarities, and then we'll get to monads, and then we do all the examples again, like properly. Okay. Yes.
Question.
Yes.
So both the name,
Mm-hmm.
using the bind.
Sorry, what?
Using the word bind.
Right, I mean, that will become clearer, but because I bind two computations, so the idea why I call it bind is I have 2 effectful computations where the effect is that there can be an exception, it can fail. I mean, maybe you can think of a maybe A as a computation that can, if all goes well, gives you an A, but it can also fail and it returns nothing. Okay, I mean, it's one way to look at maybe. So for example, looking up, this lookup, I mean, you have a lookup table and you look up and that can fail if you don't find the key, or if you find the key, it gives you the value back. And if you look at it like that, now you have 2 effectful computations where the second one can depend on the result of the first one. So this one, if it succeeds, gives you an A, and then using that A, you have a second one that can go wrong. And basically this bind maybe tells you how to do these 2 things in sequence. That it binds them together. First you do the one, then you do the other. In our transaction example, the first one is looking up the sender, and the second one basically is looking up the receiver, for example. And both of these can fail, and now and in this example, looking up the receiver, it wouldn't depend on the sender. But the overall thing depends on the sender because in the end, we update the account as well of the sender anyway. And the idea is, how do you do that? I mean, you have 2 computations that can go wrong. So you do the first, if it goes wrong, you immediately stop because it's already wrong. But if it succeeds, you have a result. You can use that result to decide what to do next, and then you do that. And that's just what this says. If it fails, it fails, and if it doesn't fail, you get a result, and using that result, you know what to do next. That's why it's called bind, because it binds 2 computations together. And the same in either, I mean, exactly the same what I just said. The only difference for either is that it can have an error message when it fails, but it binds 2 computations together. And also the same for state. You have two, I mean, the effect is different. So in the first case, the effect was that it could fail or fail with an error message. For state, the effect is that it can read and write state. So it's different effects, but you could interpret both of them or all three of them as effectful computations. Even though it's all pure Haskell, of course, it's not really a side effect, but I mean, one way to look at it is like it has these effects. You simulate these effects like exceptions or state in pure Haskell. And so you have two effectful computations where the second one can depend on the result of the first. And how do you bind them together to a longer computation that does both steps? That's why it's called bind. Okay? Other questions? Okay. Let's have 10 minutes break. Thank you.
Now, okay, there's no. Should we do list then? Or?
Yes. Okay, let's continue. One more example. Let's say I have, before I can do the last example, there's a function we haven't seen yet. It's called words. It takes a string and turns it into a list of strings, and it just splits a line into words. So if I do words, Haskell is the best programming language, then it just splits it on spaces into words. So that's in the prelude. And so let's say we want to write a function word lengths given a list of lines of text, list all the word lengths of every word and every line. What was that?
It imported the aspect. Every time you finish with a point,
Whatever. Let's call it whatever, word lengths. So it gets a list of lines of strings. It returns in the end a list of ints. One int for every word in this text. And recall this concat that I explained yesterday, I think. So concat takes a list of, I mean, it's foldable T, but you can think list again. So a list of lists and flattens it into a list. So for example, concat, I mean, yeah, I like Kenya. So this is now a list of lists of characters, and it returns a list of characters. And we have map, I mean, that we learned in the first hour. So we can first map and then concat. And there's also, I mean, that's built in, it's called concat map. So if you have a function from A to list of B's and a list of A's, it returns you a list of B's. So you first map the function, so you get a list of B's, and then you use concat to flatten that. But it's built, I mean, in the prelude, and it's called concat map. So it first maps and then concats. So for example, I could do the same thing. I mean, I had an example yesterday. What?
uppercase.
Yeah, but it should return a list. So I can do show, for example. I mean, show takes, okay, let's do concat map show of a list of ints. So if I just map show over this list, I would get a list of 3 strings. The string containing, I mean, 3, 42, and 1007. But if I then concat, I get all of them like concatenated. Anyway, so what can I do? I mean, I must, for every line in, let's call them lines. So I take the lines and I concat map. So now comes a function that takes a line. So once I have a line, I can apply my words function to the line. So now I have the words, but again I concat map. So now I have a word. And now I just return the list that just contains this one word, the length of that one word. Why is this now? Oh, sorry. Indentation should be fine. Second. Maybe lines is, yeah, because lines is a built-in thing. So I think that's the problem. So I shouldn't call it lines, I should call it lines prime. But that didn't help. Oh, because it's flip concat map basically. I mean, concat map is the wrong way around. It first takes the function, but I can't. Okay, the problem here is that that it's the wrong way around for me. So let's call it bind list. So given a list of A's and the function from A to a list of B's, give me a list of B's, and that's just flip concat map. Sorry. So now I replace this here with this bind list. Okay. And let's first try it. So word length. So I need 2 lines. Okay, I like Haskell. And Kenya is great. And this is now, I mean, all the length of all the words in all the lines. Okay, and now of course you can ask again, why bind and what does that have to do with what we have done before? And in this example, it's somehow not so clear. I mean, it's a bit silly. But one way to view lists is, I mean, we were talking about computations before. So in maybe and either, we had computations that could fail. And in state, we had computations that could use mutable state. So if you want to view lists as computations, you can see them as computations that are non-deterministic, that can have more than one result. And this basically says, okay, you have one non-deterministic computation, and given the result of the first one, await another non-deterministic computation. Then again, you can execute one after the other to a combined non-deterministic computation. And as I said, in this case, this image of non-deterministic doesn't really make sense with the lines. But I mean, that's a way to look at it, and then it makes sense to also call it bind. Anyway, and now we have like lots of examples. So let's revisit them and just look at all our binds. So we had this bind maybe. It just then we had the bind either. And we had the bind state. And now we had the bind list. And now let me align out of this. And if we recall from Friday, we had, for I/O, we had something that I also called bind. It took a side effecting computation with return type A and A to IOB. And I said that was the most powerful combinator for I/O. That we saw that with given that one, you could implement all the other things except for return. Okay, and now of course, I mean, hopefully, if you look at this, you will see a pattern. So even though these are completely different things, I mean, the maybe and either are things that can go wrong. State is something that can mutate state. List is indeterminism, and I/O is like real-world side effects. Nevertheless, for each of those, we have a function with this signature, and this function was very useful. It helped us write code involving these types in a much more compact and concise way. So it's always the same. I mean, you have something in this type that results in an A, then a way to turn, I mean, if you have an A, another of these things that result in a B, and you can combine those two, sequence them, bind them into something of these things that returns as B. Okay, and so this, the process of of realizing that you have this common pattern and like giving it a name and turning it into a type class, that's a monad in Haskell. So I'm not sure whether I should, maybe I can just write it down, the definition. So we have a class monad. Normally it's called lowercase m, but that's just convention. And we have this bind, and actually it's this. So the one we know from I/O. So we have some computation in our monad, and of result type A, and a way to, if we have the result, another computation of result type B, and we can bind the two together. I mean, it's not completely correct yet, but basically that is what we can, I mean, get from these examples now, this common thing. And actually, if we ask for, I mean, I avoided that on Friday, I think, but if we ask for the type of this bind operator that we saw for I/O, then incidentally we see it's not defined for I/O, it's from this monad. So I basically was keeping that from you, that this is much more general than just for I/O. Okay, and right, so that's a monad. So in its essence, a monad is some concept of computation with some special thrill. So for example, computations that can fail, or computations that can fail with an error message, or computations that can make use of mutable state, or computations that can be indeterministic, or computations that can have real-world side effects. And then the idea is you want to somehow combine these computations to more complex computations. So if you have one of these things and a way to use the result of the first to have another of these things, then you can sequence the two, bind them together to a bigger computation. And how that works is completely dependent on the monad. So for I/O, this is built in, that's like deep magic in the compiler, so no way for us to implement that. But we saw for maybe and either and state and list, we could implement it ourselves, but it was completely different concept. So I mean, so the idea for maybe and either is that you do the first computation, and if it goes wrong, you immediately stop. Whereas the idea for state to bind two together is that you thread the state through the two computations. You update the state with the first computation and then feed it into the second computation. The idea for list is this concat map. So if you have something indeterminate, so you have many results, you apply the continuation, what to do next, to each of the possible results, and you get a bunch of new results for each, and you flatten them all into a new result list. And finally, for I/O, the idea was you execute the first plan. Oh no, the plan is first it's the first plan, the side effects of the first plan. Then when you execute that, a plan that first executes the first plan, and then if it gets a result of type A, knows the second plan and execute that afterwards. So it's like in all these cases, maybe either are similar, but in principle it's like completely different ways to combine things, and it depends on what you want to combine. But nevertheless, it gives you this way to combine simpler computations into more complex computations. That's what monad is. And that is also, we had this programmable semicolon before, that we said that the dot, the function composition, is something like the semicolon in imperative languages. People also say that this bind is like a programmable semicolon, because in an imperative language, basically you have statements one after the other, and what happens between two statements, that depends. For example, if you throw an exception, then execution is stopped. And if not, then you continue with the next statement. And so that's basically what the semicolon does. It binds statements together, one after the other, and in a sense, this thing does the same for arbitrary monads. So in that sense, Haskell has a programmable semicolon, because you can give different meanings to what it means to bind two statements together. And that depends on whether you want to throw exceptions, or have mutable state, or have real-world side effects, or indeterminism, or whatever. But actually, those are like the main examples already. One is missing, like read-only state. But we could implement that, of course, with this. But that's basically, if you understand those 5 examples, you in principle understand. There's one like weird monad, but we are probably not even talking about it in this course, continuation monad. But apart from that one, basically all monads are just variations on these somehow. We will later see how one thing is, you may say that, that you now have a problem where you have, you want to throw exceptions and you want to mutate state. And that's also possible. So you can combine monads to other monads that then combine the effects of the two. So basically you can mix and match or plug and play different effects that you want together. But we'll get to that later. Right. And one super good news is that this do notation that we did for I/O on Friday, that doesn't just work for I/O, it works for any monad. So maybe next would be that I rewrite the examples in terms of do notation. One problem is, so there's a couple of problems. The applicative one is a problem. And so actually, if you look here, the monad class has a superclass applicative. So actually the definition is this. And actually the definition of applicative is sorry. And there are two things, pure and something that I never know how to pronounce, maybe app. So that has a bit of a weird signature. It's and it complains now because that clashes with stuff from the prelude. I could hide it, I suppose, but then I don't have do notation. So
maybe just comment it there.
Yeah, I just commented. Okay, we haven't talked about applicative at all. Functor, you know. But this applicative is completely new. And this is also, it's all a bit convoluted, the history of Haskell. Basically, now people understand that there's like a natural hierarchy of type classes. So functor is like the most common one, but the weakest. Then there's something stronger called applicative. And then the strongest is monad. And it's this natural hierarchy. But historically, applicative was discovered like much later than monads. So historically, in older versions of Haskell, this applicative didn't appear. And then later, people realized that applicative is also important and built that in, and this is still ongoing. So between GHG versions, things shift slightly around. But for example, we already saw on Friday that once you have this bind for I/O, you can implement liftm in terms of bind, and that liftm is just fmap for I/O. So basically the idea is that once you have this bind and the pure, everything else like the functor instance and this thing here, there's a default implementation basically. So you only have, bind is the most important one. But you also need pure, and pure is the one, I had that in state. So the idea of pure is, you have this concept of computation, whatever, it can throw exceptions, or it can mutate state, or it can have real world side effects. But you don't have to use these computations. You can have a computation that could throw an exception, but it doesn't, it just returns a value. Or you could have a computation that is allowed to use state, but it doesn't, it is independent of the state. Same with I/O. We had this return, which is a potentially side affecting computation, which doesn't have side effects. That's this pure. So it's pure because it's a pure value, even though, so you can take a normal value and lift it into this computation, but it doesn't make use of side effects. So that we basically all have seen, so this remains. And that looks a bit mysterious. But if we look at, maybe I should first, I don't know, maybe I should first write it. So we come back to this applicative, to this one here. I first would like to write it in do notation because then it looks nicer. I'm just trying to think what I have to do for this to make that work for state. For state I could write an instance actually. Okay. So and it turns out, if we ask for information for monad, then either and list and maybe and I/O are already instances. So we wouldn't have needed to define our bind maybe, bind either, bind list, because that's already in the prelude. State is not in the prelude. That is in like a very commonly used package, but it's not in the base libraries, and it's defined slightly differently, namely with a new type. But maybe I don't do. Should I do this?
You won't have do notation if you define it.
No, I could write an instance for this, but okay, fine, yeah. So actually, I wanted to keep it simpler, but actually the definition of state is with a new type around this. So it's state, and then record syntax, run state, like so. So it's like at runtime the same as what I told you, but there's this new type wrapper around it. And then of course, one has to slightly modify all of this by always carrying this new type constructor around, wrapping and unwrapping as appropriate. But the good news is, sorry. The good news is that I don't have to change this label S, because I only use this get put pure and the bind, and I didn't explicitly use the constructor, the definition of state. So I don't have to change any of this here. The second problem is now I have to import MTL, for example. So if I want the monad instance, the built-in one, I need a library, so let me change my my dependencies. It's called MTL, or one of them is MTL. Let me just reload. For monad transformer something?
Library.
Library. Okay, and now I don't have to, I can comment out the state definition. And this bind, I mean, that I can bind state get put pure. And now I must just import that. And the module is called control monad state. And now I will get a couple of errors because this bind state is of course not called bind state. This is now the actual monadic, I mean this operator thing. I don't know why my stupid cursor keeps jumping. Oh yeah, and the pure is just pure, not pure S. Okay. Right. So now basically I have all the, I mean maybe either list are anyway monads in the prelude already or in the base libraries, and state is in this MTL package. Right. And as I said, this applicative, we will talk about that in a bit later. First I want to show you that now with the do notation, that we can use that now. So let's go back to our, let me not use this, okay. Let's check, maybe I can still use, okay. We can worry about that in a second. Okay, let me copy this again, this process transaction, and maybe now call it M for monad. And now use do notation. So do, it's old from. So as I explained on Friday, with do notation, we don't need the in anymore for lets. So we can just do right. So that would be this in do notation. And one other thing I can do, the just in the case of maybe, or the pure is, the just is just pure. So, I mean, in the maybe monad, the side effect I have, or the effect I have is that it can fail, and just is not failing. So that's pure. So for maybe, just is pure. So I can write that as pure if I want. It's the same thing for maybe. Okay. And then there is this one annoying thing still with this check maybe, which I said is somewhat non-standard anyway. And I mean, of course, and at some point I should go to the slides because there are stuff as well, but I want to maybe finish this quickly. Right. So I mean, one question of course is, why do we need monads? I mean, I can have my bind maybe and my bind state and everything. I mean, first of all, it's always a good idea to identify a common pattern. I mean, that if you realize that things like are similar or that there is the same pattern, it's always good if you realize that and give it a name. I mean, naming things is very powerful, and so is that. Then, of course, it's just convenience. You don't have to remember all sorts of different names for the bind operations, bind maybe, bind state, bind whatever. It's always the same operator. In the case of, I mean, this is true for all abstractions, like functor, for example. But in the case of monads, there's this special built-in syntax with the do. So that's another advantage of using monads. And finally, many things you can do for any monad. So there are operations that make sense not just for special monads, but for any monad. And so you can define them once and for all, and then have them available in every monad. So you don't have to define it several times. And one such thing is called when, which is not in scope. That's good, so we can implement it ourselves. But it is it's in control monad, so it's in the base library, but let's just define it ourselves. So that works actually for an arbitrary applicative, but let's just do it for an arbitrary monad at the moment. So it takes a Boolean and an M unit and produces an M unit. The idea is I check the Boolean if it's true. So let's say B and action. So often we call, I mean, in Haskell, a function that returns unit is useless, because we know, I mean, if the return type of a function is unit, we know there is no I/O, so it can't have side effects. So it must be a pure computation that results in a unit, and unit only has one value, namely unit. So we don't care what, I mean, the function is just constantly for anything you put in, it returns unit. So you will never see in pure Haskell a function that has a return type unit. But you do see functions that have a return type I/O unit, for example. That just means it's like it has side effects, but no interesting result. That's like in imperative languages, functions that have void. So I mean, that's similar. And the same is true for any monad. So I mean, just a unit wouldn't make sense, but an M unit can make sense. So that means it's only interesting for its effects, not for its result. And the idea of this when is, so when, I mean, if B is true, we perform the action, and if not, we don't. So true action is action, and when false, I mean, this is now the standard pattern on bool again. I could, of course, also do it with if then else. So how do we not perform the action? Well, now we know a way to have a computation that doesn't have any effects, namely with pure. So we can just do pure this. And actually, and we see we only use pure. I mean, the only special feature of monad we use is pure, and that is already defined in applicative. Therefore, we can just as well do that for applicative. Right, and this is very nice because, I mean, this is like, I mean, I said in the beginning when we talked about if then else that in Haskell there's always an else branch because you have an expression, so we must have a result in both cases. But in imperative languages, often you only have an if without an else because the thing doesn't have a result, it just does things or not. So if the condition is true, you do stuff, and if not, then you just ignore it. And the when is like this. So in a monad, you can do this. And once we have this, we can now rewrite our check maybe. We don't need this check maybe anymore. So we can use when, and there's actually another one. It's called unless. And unless be action is just when not be action. So we can eta reduce the action. Why? Oh, okay. It's defined in state. So let me hide. Okay. Right. So let's see. So here, for example, in this example, we've checked this condition. And if this condition is true, we want it to stop. and otherwise we proceed. That was how this check maybe was defined. So using when, I can now rewrite this. So I can do the same thing, the whole thing in a do block. I can say when this condition is true, we break, we stop, and otherwise we proceed. So now I'm already rid of one indentation. I don't need the dollar, and I could, I always write it like this. I always write the when in the first line and the action in the second. But of course, this line would be short enough to write it like this. I just find it clearer this way. Okay, and here we have the same thing. So when old from less than tx amount, nothing. Right. And now this is, I think, the best, almost the best form we can get it in. Right, and this now shows also, okay, so that's what was now for maybe. So now knowing that we know that maybe is a monad, so we can use do notation, and we can use when, which, as you see, is defined for any applicative even, so you always have that available. We can now write this very nicely. And this now really looks almost like an imperative program. So we check this condition. If it's true, we stop. Then we look up. This is now something that can fail, but this is all baked into the bind now. So we don't have to explicitly worry about this case. We don't have at each step that can fail say, okay, if this step fails, we stop. Otherwise, we continue. This is now baked into the monad instance of maybe. Then we check this condition. If it's true, we stop. We again potentially failing computation, look up the amount of 2, and we can do let, and then finally we return this pure value, which can't fail anymore at this point. Basically, what you could also say, it's only like the happy path. So we don't have no longer have to worry about what happens if a lookup fails, because it's this is built into the bind now that we stop at that point. Now let's look at
it leaves like the actual logic, the business logic.
Yes.
And hides the.
Yes, one way to look at the very first version of this is that it's somehow a mix of business logic for this specific example with my transaction type and my bank type, and general maybe stuff that you always do. If something fails, you stop. If not, you continue. So this is like a mix-up, and it makes it much more difficult if you see this code to see what's actually going on, what's the business logic. Whereas if you look at the last version, which for whatever reason I should have written it after the when. So this is now basically just business logic, almost just exclusively business logic. And the handling of the exceptional cases is implicit in how maybe works, how the monad instance for maybe works. And we can now try to do the same for this either case. So I can't call it M because now EM maybe for either monad. Right, so let's do the same thing. This here is actually not too bad, the discards. That's fine, I suppose. I could do it with when, but doesn't really make it nicer. Okay, but now let's do notation. So old from gone. Now now this I can do with when again. So when old from an amount. Okay. Okay, sorry. Must get the indentations right. So this is all 2. In is no longer necessary. And for the either monad, pure is right. So the case where either can throw exceptions with error messages, but if it doesn't, then it's right, that's pure. So yeah, that also fits on one screen now. And the indentation is gone. I mean, there's still this one level, but I could have written these first lines with when as well. Maybe I should, just for fun. So if I wanted to do everything with when, then I could, okay, the first. Right. So now, as I said in the beginning, like this dangling, if it goes, your code moves further and further to the right, that's normally a bad sign. And now we're completely rid of that. So now it's, I mean, basically one level of alignment for the whole time. And now, and one other nice thing is, I mean, we see that these two are now very similar. So basically one, I mean, if you had written this and then at some point decide that it would be nice to have error messages, with this code it would be very simple to change the maybe to an either, and then you just have to do like small changes that whenever you fail here with nothing, now you have to throw an error with an error message. And I mean, this lookup, we had this modification that it must also produce an error message. But the structure of the code is now completely the same. I mean, the code is almost identical in the both two cases, which is also nice for monads. So we will, have another lecture about monads where we will emphasize this point that basically you can change the monad without needing to change your code, or at least not too much of your code, which is also nice. And okay, that was that. Now the tree labeling stuff. So we were here. Sorry. I mean, that already looked nice, relatively. But now let's also use, let's call it label SM for state monad. And let's also use do notation. This. And that. So it's, I mean, it was already quite nice before, but now it's even nicer. Okay. And hopefully it will all still work. I mean, if we reload, we get errors, great. Yeah, I have to restart the REPL because I added this dependency. Okay, no worries. So run state, label SM tree 1. Sorry, I must do label SM tree and then I get a state, so I must unwrap it because it's now a new type, and provide the first label. And it looks almost as, or exactly as before. I mean, so we didn't change anything.
We have a 4 on the other side.
Right, okay, I made that wrong. That was my mistake. I should have put this, I thought the state would be first. But it seems in this control monad state, they put it at the second position, which doesn't make a difference. Right, okay, so that's state. And finally, we can also write our word count thing, word lengths in do notation. Because list is also monad. So if you use do notation there, it's always mechanical. I mean, that is really mechanical because, as I said on Friday, the compiler does that in some pre-processing step, purely mechanically replacing do notation with binds. And in the case of, I mean, what is pure in the case of lists? So as I said, pure means you have a potentially effectful computation that doesn't make any use of the effects. In the case of list, the effect is that you can have indeterminism. So you can have more than one result or no result at all. So what does it mean in the case of, I mean, you could potentially have indeterminism, but you don't make use of that. Well, that means that you just return a list with one element. So there is a specific, unique result. So therefore, pure in the case of lists is the function that just returns the singleton list with one element. So we could write this as like that. And yeah. And because lists are so useful and ubiquitous in Haskell, there's a special like do notation for lists that's called list comprehension. So let's do a third version just for lists. So this is not available for the other monads. That's special for lists. But if you have a mathematical background and you set notation, then that should look hopefully quite familiar for you. So one way to write that would be, or another way is length word. I mean, you can write it in one line, of course, but maybe it's clearer to do it like this. Yeah, so that's list comprehension. So instead of, I mean, it works like this. So you have, I mean, this vertical bar, and then you can have these generator expressions which correspond in do notation to the bind. And you can also have conditions there that's specific to lists. So you could have check, for example, whatever, only consider lines that are, I mean, you could do something like, you can write stuff like, whatever, length line greater 100 or so. So you can have conditions in there. And you can have several of these expressions. And you can have lets in there. And then before the vertical bar, you write what you actually want in your list. But this is, again, basically just another syntax for the same thing, specific for lists. So, yeah. Right. And maybe I should now do the applicative stuff as well. And get it over with, and then we can go through the slides and see whether we missed something. So there's one more thing. I mean, I was vague with this applicative, especially this thing. And if we now look back at our code, especially this here, this is a relatively common pattern. So we have a bunch of binds, in this case 2, that don't, I mean, where this one here, the R prime is completely independent of the L prime. It doesn't mention the L prime here on the right-hand side. And then, so we have this, and then in the end, we apply some pure function to those intermediate results. And this is exactly where applicative shines, So in the last version, maybe call it label SA, where I now use applicative. I could write this here more compact as node label SL. Right. And this, I mean, on the slides it says it's a nice exercise to see why this works. Because it's not, I mean, to me, when I saw it the first time, it wasn't obvious why this type here, what that has to do with what I just did. I mean, we could, I'm not sure whether I should show why this is now correct, but, or maybe not. And, okay, and one thing is, I mean, so we have this applicative here, but you never have to implement this by hand, because that, there is something called app, which has, so if, I think this is not in scope now, that's in control monad, so that's predefined. So if you have a monad M, then you can write something with the signature. So M of A, this signature. So we have something of type A to B and MA to MB. And this is now simple with do notation. So you have some like effectful function, a computation that results in a function from A to B but can have effects, and some effectful argument. And what do you do to get to an effectful B? Well, you bind, I mean, you basically execute the side effects of the MF to get to your function, and you execute the side effects of the MA to get to your argument, and then you apply the F to the function. And this is not control, of course. That's, I don't know why I write that. It's monad. Okay, and that means once you have a monad, you can implement this here by just using this up thing. So if you have a new monad that where you want to write an instance for, then what you have to do is you have to implement pure. So you have to So you have to say in which way you can have a computation that doesn't make use of any effects, and you have to implement bind. And everything else, the fmap from functor and this thing, then you can just as boilerplate, where you don't have to think about it. But that's also on the slides. Right. And I mean, as for the difference between, so we have functor implies applicative, applicative implies, I mean not implies, it's a superclass of applicative, applicative is a superclass of monad. Which means every monad is applicative and every applicative is a functor. And of course the question, and we have seen a couple of examples of monads, and of course then they are automatically applicative and functors. But there are not many examples of things that are applicative but not a monad, but there are examples. So this is like not the same thing. So bind is strictly more powerful than this, whatever you pronounce it. And I mean, you can see that from the signature. So the point is a monad, I mean, this bind, if you bind two computations, the second computation can depend on the result of the first. So you first need to do this first computation, you get a result of type A, and then you know what you want to do next. So what you want to do next can depend on the result of what you have done first. But in applicative, as like in this example here, you already know that you will do this computation and that. So this one here does not depend on the result of the first one. So that is weaker. But it's a very common case. So very often you only need applicative, but sometimes you need like the full power of bind, where what you want to do next really depends on the result of the first step. So there is a difference. And there are types that are applicative and not monad. So they are less powerful, but often powerful enough. And there are examples, I mean, because of this, I mean, it gives you less power, but it also gives you more possibilities. So for example, you could parallelize that. In principle, you could run this computation and that computation on different machines at the same time and then combine the results afterwards. Whereas if you really use monadic bind, where the second computation depends on the first, you of course can't do it in parallel. You first have to execute the first one to wait for the result, and then you only then do you know what the second one is. Right, so there's a trade-off. Anyway, and now that's that, and I think now I can switch to the slides. Okay, so maybe this is a similar example, I think. It's a different example, but I mean, for maybe. So we don't have to look at the example. It's basically the same thing, that you get these dangling stuff and then you can make that nicer. Then either, same thing, what we did, throw error. I didn't do catch error. So you can also implement that. So given a computation that can potentially fail and the handler, then it does the obvious thing. I think I maybe don't need to do this now. I mean, the implementation is on the slides if you're interested, but we didn't make use of handling exceptions in our example. And here's state, so on the slides there's a different example. There's also the tree labeling example, so that should be more or less the same, but this is some like adventure game example. Whatever. And yeah, maybe this is quite nice. I mean, I mentioned that I mean, it looks very imperative now. I mean, if you replace this bind error with something like that you would find in C# or so, with this colon, this assignment operator, it very much looks like imperative code. Get put, whatever, label 3, list, we did. Okay, the examples, monads. Okay, our monad class. And I mean, the name monad, that somehow I think originally comes from philosophy, but then it's also a mathematical term from category theory. And it has something to do with monoid, but we haven't talked about monoids yet, so that doesn't really help. But I mean, there is this joke, which you probably won't find funny, but I mean, I think there are even t-shirts, that a monad is just a monoid in the category of endofunctors, so what's the problem? So if you are good in category theory, then it's all, I mean, it's simple. And like Phil Wotler and Moji have made that popular in functional programming. Of course, you can, I mean, it's quite a, like, I mean, in mathematics, I mean, it's not particularly common or special or anything, but it was basically genius of Moji and Wotler to realize that in programming it's an extremely useful abstraction, because it allows you to sequence things together. Right, so we have this. Yeah, and I mean, I did this new type. So in Haskell, you can't make an instance of this directly. But that's just this. Right, and I already mentioned, but I mean, those are more or less the most important ones. There's like reader still, which is read-only state that you can read but not write. So that's useful for something like configurations. Often you read in the beginning of your program, you read a config file with a bunch of settings, and then you pass that around everywhere. And using the reader monad, you can make that nicer, but it's like strictly weaker than stakes. So if you understand stake, you also understand reader. And then as I also already mentioned, there's this continuation monad, which we will not talk about, I think. But apart from that, everything else is just combinations of those. Writer. But that's also basically a special case of state. Yeah. Did we see more? Which one? Okay, right. Okay, and I mean, one of the reasons I was a bit uncomfortable yesterday with explaining this generator stuff is that gen from QuickCheck is also a monad. So I was always tempted to use do notation, but I couldn't because I hadn't explained it yet. So there are more. So gen is also a monad, and in principle, you can think of it as a state monad. So the state is like the random number generator seed, and the size you are currently building. So that also helps to know this, because then, I don't know, should I go back to this? But we still have plenty of time. So maybe after the next break I can, or at some point I can go back and do this nicer with the binary trees, the arbitrary instance, using now that the knowledge that that's actually a monad. Right, maybe we should talk about that and then make another break, monad loss?
Yeah.
Right, so remember when we talked about functors, I told you there are two laws, that fmap of the identity is the identity and fmap of a composition is the composition of fmapping. And for the monad there are also laws. And they are unfortunately a bit messy, even though they mean simple things. I mean, if you understand this thing that a monad is just a monoid in the category of endofunctors, then the first thing basically means that return is a unit for this monoid, and the second means that bind is associative.
You said that return is the same as pure?
I'm sorry?
You already said that.
Oh no, maybe not. Okay, this is, I mean, but I did say that historically monads came first, and then somebody discovered this applicative concept or abstraction and discovered that that is useful in its own right, because there are things that are applicative but not monad. But traditionally, so monad had the bind, but also something called return, which we saw for I/O. But in applicative it's the same thing. So the idea of pure and return is exactly the same, that you take a pure value and see it as an effectful computation that doesn't have any effects. But the name of pure, I mean, in applicative class is pure, and in the monad class was return. And now recently in the newer GHC versions, they changed the monad class and threw a return out. Or didn't throw it out yet, but you no longer need to implement it. It has a default implementation which just defines it as pure. So return and pure should always be the same. And the plan is that in like future versions of GHC, return will be taken out from the class completely. And as I already mentioned on Friday, return is misleading especially for you if you're used to imperative programming, because in imperative programming, if you have a long function and in the middle you have a return, then you would expect that execution stops at that point and the function returns with this value. And that's not what this does. You can have a return in the middle and it just doesn't do anything. But that's always misleading, because it looks as if it would stop there. So probably it's better to these days, instead of return, write pure. But the slides are a bit older, so it still says return, but you can think pure. So basically the first thing means that return is a unit for bind. Yeah, whatever. But the point, I mean, this looks complicated, but it's actually, I mean, one way to look at it is that refactoring works as you would expect. So if you have like a long do block and you somehow split it into 3 parts or 2 parts, then and define like extra functions for those parts, then it doesn't matter where you split the do block. I mean, the result is still the same. So if you group, like, if you take the first 2/3 in its own function and then do the rest, or if you only do like the top and then last 2/3 is the rest, it doesn't matter. So yeah, that's what the associativity says. And this is just an example. So I mean, as I also said on Friday, the Haskell type system is not powerful enough to prove these things. So it's basically just a comment. So it's like a contract between a library writer and the user of the library, that the library writer should make sure that these laws hold for the instances he writes, so that the user can rely that they hold. And normally it's things that, yeah, that feel as it should be like this. So it would be very surprising if you had a monad that wouldn't follow these laws. And you can't prove that in Haskell. So if you want to prove it, you have to prove it manually. And here on this slide, we have an example of proving this first law. So it says if I return and then bind the continuation f, then that is the same as if I simply apply f to a directly. And we can just prove that by hand. So if we start with this, the left-hand side, and now we plug in the definition of bind for maybe. Remember that we do a case on this maybe value, and in the case of nothing, we immediately stop, and if it's just x, we continue with our continuation. So now return in the case of maybe is just. So we can replace return a with just a, which means in this case statement, the first case doesn't match, the second case matches. So we do this, so x is bound to a, so we get fa. And okay, I think it doesn't prove all of them. Okay, the second one, so that m bind return is the same as m. So just as an exercise, how one would do such a proof. So again, we plug in the definition of bind. So we pattern match on the m. If it's nothing, we stop. If it's just x, we return. And now the definition of return in the case of maybe is just. So we can replace this return with just. And then we see that no matter what m is, we just return m itself. So that's the same as m. So if m was nothing, it's nothing. If m was just x, it's just x. So this is just m. So that proves the second monad law for the case of maybe. And on the slides, there is no proof of the third one. But I mean, if you enjoy it, you can, of course, do it. The point is just to show that one can, this all looks like very mysterious. But if you just step by step plug in the definitions and do it slowly, then you can prove these things if you so desire. Of course, you don't have to do it for these things because, other people have already proven that for all these common monads. So in practice, I've never proven any of that. But if you get more experience, you get a feeling for whether it is a monad or not without actually having to write down a proof. So that would only be maybe if you want to publish a scientific paper on some cool new monad you discovered. Okay, so that's that. Oh, he does prove the last one. I'm not sure we want to do that. I think that's someone. So on the slides there's a proof of that case, but I think this is not very interesting. Right, this one we also saw on Friday already. That was the first combinator actually for IO that we introduced. And we pronounced it then. So the idea was you execute the first plan, forget the result, execute the second plan, and the overall result is the result of the second plan. And this is also not specific to IO. You can define that in any monad with bind. In the same way we defined it on Friday for IO. So you just use bind and you ignore the result of the first computation. Do notation, we saw. Do notation. We made the labeling nicer. Okay, this I haven't mentioned, but it's easy to do. Maybe let's switch back. When we ran this thing here, we use this run state, and that gives us back the result of the computation and the updated state, which is 4 in this case. And this evil state basically just throws away the state. So if you're only interested in the result, not the new state, then there's this evil state. But that is already defined in, because I imported control monad state, so that's already defined in that library. But of course, you could easily implement it yourself. You just do run state and then compose it with first. So you forget the second component of this pair and just keep the first. So instead of doing this here in my example, I could just have used evil state, and then I would just get the label tree and not the 4. And there's also a version that throws away the result and just keeps the state. That's called, don't know, something. Okay, I mean, we did it from 1, so that's basically the same thing. Okay, run state we just did, whatever. List comprehension I just showed you as well, so that for special case of lists, there's yet another notation instead of do notation that is often used, but it's like just another syntax for the same thing. Right, so I mean this list comprehension is often the shortest way to write these things for lists, so one should use it. And yeah, this I just said, that return is misleading and it's just a normal function. It doesn't have any, it doesn't stop the execution or anything like that. And I mean, there was a question on Friday, somebody was confused that there was another do needed. And basically this is to that. So you don't always need a do if you only have like one line, like put string line last. You don't need do put string line last. Do is only useful if you want to bind something, but it also doesn't do harm. It's just in an idiomatic Haskell. And on the other hand, sometimes you need like several do's, like in the branches of an if. Then if you would need new do's. But we saw that on Friday already. Okay, and maybe this I can still say, and then we make a break, and then we can talk about these things. So I/O. As I said, I mean, I/O is deep magic. So that's, I mean, all the other examples of monads we could, I mean, they are defined in the base libraries or in some commonly used packages like MTL, but we could have defined them ourselves in Haskell. There was no magic about it. But I/O is built in. So I mean, that is really with the runtime system. I mean, to execute something in I/O, I mean, the runtime system has to do something special. And you cannot escape from I/O. I mean, you can, but you shouldn't. So that we looked at briefly at this unsafe perform I/O, which does have this signature. But I mean, you should never use that. So in principle, once a computation is, you have an I/O in your types, then you can't get rid of it again. So that means once you use side effects, you use side effects. You can't later unuse side effects. Once they're used, they're used. But that is normally not true for like our other examples. I mean, there are ways. I mean, for example, with run state or evil state, we can get rid of the state pair again. So we have this effectful computation, but in the end we get a pure result. So I/O in that regard is special. And what is special about is this. Not that it's a monad. I mean, there are many monads as we saw. The special thing of I/O is that it's like primitive and built into the system. So, I mean, it's mostly special because it can do side effects and not because it's a monad. So even if you don't know about monad, you could still write programs that do side effects. Right, but we talked about all of that. And one interesting fact is maybe, I mean, I can demonstrate that. If I ask for I/O, I mean, even though we just said it's primitive, that's actually a lie. Because it's not. I mean, it's just a new type around something that looks horrifying. But if you squint, maybe, I mean, one could import all of this, then it looks a bit less intimidating.
JC print is a single library, JC print.
Yes, so let me just do this so that you're not.
There in Kava,
I'm sorry?
in the REPL. So
Oh, yeah, can I? Oh.
I think you can. Or you have to be.
I mean,
no, it's not part of it, sorry.
So let me just, I mean, one shouldn't normally.
It's part of base, I think.
Maybe. Yeah, you're right, actually. I think
Right,
it's.
I think it's part of base. No?
No, sorry, import.
No.
I think it's, isn't it in GHGX? Yes, sometimes. I mean, some of it. Let me see. Okay, no, okay, fine. But it looks a bit better now. I mean, this is still a bit weird, this thing. But if you ignore that, I mean, it's just a new type wrapper. And if you look at what it wraps, it says something like state real world to state real world, comma A. So internally, I/O is modeled as like just a state monad, where the type of state is the real world. I mean, just the world. So basically, what that says is that, I mean, I/O computation is just like a pure computation, but the input state is the whole world, and then the computation can change the whole world and return a result. So I mean, I/O is like, you can think of it like a special state monad. Of course, I mean, it's deep magic because we can't really thread the real world through our laptops, but I mean, it's sort of made like that. Okay, and maybe we should have another break, and then we can look at some more of these. I mean, I showed you the when, but there are many more like things that work for every monad, not just for I/O.
That come for free when you...
That come for free. Once you have identified something as a monad, you have a whole slew of interesting and useful functions at your disposal that you can use. Right. Okay, but I think we should have... Yeah, sorry, yeah, of course. Are there questions?
There's a slide that says that you can't make an instance of monad.
Sorry.
There's a slide that says you can't make an instance of a monad.
Yes.
I didn't...
An instance of a monad. I mean, defining an instance of a monad.
Oh, yeah, yeah. Sure. Just to maybe read. Yes. So how you would define? Oh, actually, it's on the slides, but I can do it. So, sorry. Where did my? Oh, yeah. I mean, another monad that we haven't seen yet. That's also useful, very useful, is the so-called reader monad. Let me just define it.
Current table.
How annoying. Okay. Let me just define it. So it can read state of... Okay, let me first write what it is. So this is the so-called reader monad, and it's, I mean, the idea is the state monad has readable and, I mean, mutable state. We had this get, which could read the state, and we had put, which could update the state. The idea of the reader monad is that it can only read but not update. So it's read-only state. And I mentioned briefly, I mean, the common use case is like for configurations. In the beginning of your program, you read some config file, and then a lot of the functions in your program need some of the settings from the config file. So you could do all the computations in reader config, and then all the computations have access to that. Otherwise, you would need to, I mean, always explicitly pass this configuration around everywhere. And I mean, remember, state was state takes the old state and then returns, actually I should, I don't know, maybe, I mean, in the libraries it's the other way around too, it's A, S. But anyway, the idea was a stateful computation takes the value of the current value of the state and then returns an updated value of the state and the result. And if we now have read-only state, then there is no updated value because we can't change the state. So we don't need this component, so it's simply a function from S to A. So, so the result can depend on the state, but you never update the state. So that's the reader monad. And if I now wanted to make that into a monad, I mean, there is control monad reader where that instance is defined. But if I wanted to do that, so I would need to functor reader R, where? And I would need applicative reader R. And I would need monad, reader R. Right. And the simplest, and so for functor I need fmap, but that is boilerplate, so you never have to write that. You can always define it as lift m, as we saw for I/O. And in applicative, there's pure and this whatever it's pronounced star, and the star you also never have to define because that's just app, and that is in control monad. And now probably because I defined that. No, but my app should work. Why doesn't my app work? I mean, I defined app, didn't I? So why does it not accept that? Because it's also in state. Sorry. So I must hide that here. So I mean, I defined that now in the slides, but that's in control monad, so you don't have to define this AP yourself. That's normally available. So that's that, and return, I don't have to define. So all I have to do is pure and bind. So let's do pure. So, and as I said, pure, the idea of pure is always you have a potential effectful computation that doesn't have any effects. So what is a computation that can read from state but doesn't use the state, it doesn't depend on the state, that's just a constant function. Or, I mean, I could write it like so. I mean, normally, so it takes a state, then completely ignores the state and just returns the given A. So that would be pure for the reader monad. And I could write that like so, and I can also write it like so. And I can even write it like so. Okay, so leaves bind. Bind is always the most interesting one. So we have some computation that can depend on state with return type A, and a continuation for whatever reason. That traditional letter for continuations is K, not C. I think because of German, because in German we write it with K, but I'm not sure. So what do you do? So you need the reader constructor, and you have given a state. So now given that state, you can, one thing. I mean, we had these special before I continue here, we had these special things for get and put for state. So we can read state and we can write state. For the reader monad, because it's read only, we can't write, but we can read, but it's not called get, it's called ask, whatever. So let me define that, then it's easier.
So it clashes maybe.
Yeah, probably. So ask is just of type reader RR. So given the state, it gives you the state. So that's just reader identity. Anyway, but now what do I do? Okay, the state, now I must somehow get to my A. So I can apply this now. So let A, so I run reader, my given thing to the given state. So now I have my A. Now I can, in KA, is it that simple? No. So I have A, so now KA is of type reader RB. Oh yeah, run reader KAS. So the point here is, in the state monad, there were different states here, because the first computation could change the state, and then when we invoke the second computation, we use the updated state. Here in the reader monad, because it's read-only state, it's both times the same state. It's always the same state. Okay, so now that's that. So now we have functor implemented with lift m, which comes from monad, We have applicative, we implemented pure. We did not implement this thing, we just used the AP. And in Monad, we implemented bind. And that's how we implement a vitamin instance for Monad. So we have to implement pure and bind, and fmap and star have standard implementations called lift M and AP. I'm, I'm sorry? Mix and match monads, we come to that. I mean, it's not that simple, but there are ways to combine monads that combine features of the two. So if you need mutable state and exceptions, then there's a way to get a monad that has both. But there will be a lecture about that.
And we are only doing this. Now you have access to the notation and a bunch of the useful functions that we're going to see after the break.
Yes, yes.
So it's just a bit of code to get a huge power.
Yes. Any other questions before we have a short break? Good. Okay. Okay, let's finish this. So if we just think back to the examples, I mean, so what all monads have in common is this pure and the bind. So that's available in all monads. But all the monads we have seen also have special features that the other monads don't have. I mean, maybe and either basically could fail. I had this throw error. State has get and put. Reader has this ask. List has this indeterminism. I mean, we didn't see anything in particular there, but I mean, that's special for that. And IO, of course, has all the actual IO stuff like put string line or read file and so on. Nevertheless, so I mean, obviously, they are not interchangeable. I mean, you get different effects and you have different operations. But just with return and bind, you can already express many useful functions that then exist for all monads. So you define it once and for all, and then you have it available for all monads. One example we saw was this when, and another example we saw was this then. So now, let's look at some more. And as I also showed you already, that for example our example for maybe and our example for either, in the end they look very similar. And so the code is almost identical, and only where specific features, I mean the specific feature of either is that you have error messages. So obviously if you want to produce an error message, the code can't be the same as for maybe. But for all other parts it was identical. So that also means that often it's easy to switch the monad. If you realize that you need a different monad with different effects, then often it's easy. You don't have to change much in your code to change the monad. Right, and this is a bunch of functions that are defined for all monads. I mean, we could also look at package. So all of this, or most of this, is in the base libraries in module control.monad. And there, I think most of them that we see on the slide will be available here as well, and then with documentation and so on. So let's see. So when we have already seen, lift m we have already seen. So that's basically fmap. How once you have bind, you can define fmap in terms of bind. So this is just fmap. Map M we have seen when we talked about I/O. I just didn't tell you then that it's more general. So it's like a monadic version of map, because if you have a list of A's, if you in a function that you want to apply an effectful computation to each element in a list, then if you just use the normal map, then you would get a list of IOBs. And then we had this sequence. It takes a list of IO. This is all for IO. There's another slide for, okay, so these all exist for IO. And we saw some of them on Friday. And the cool thing now is that all of them are actually much more general. So they don't just work for IO, they work for arbitrary monads. So for example, this map M, that is if you want to to map an effectful function over a list. So I mean, we saw it for I/O. We had this example to ask several questions and collect the results. So now, for example, we could do. No, we can't. I think. I'm just trying to think. I mean, we could label like several trees, for example. Yes, if we have something simple for maybe. Yeah, okay, let's see. Yeah, as an example, let's take maybe. I mean, we have our lookup, our T lookup. So let's map M, the function that given a name of an account holder, applies lookup as in bank. And now we can have a list, for example, Robertino and Karina. What was it called? Bank 1? Bank Prime?
Initial bank.
Initial bank. Right. So I mean, we had this lookup function. Maybe it can fail if the person doesn't exist. And now, so it's an effectful function, and we can now map that over this list. And so if we just mapped it, not map-emped it, then we would get a list of maybes. I mean, we can do that as well. So now we get a list of maybes. But with map-m, we sequence all these these results into one maybe. Which means if one of those, so if, okay, so far so good. But now if there was somebody that doesn't have an account at that bank, like me, if we just map over it, we get just 100, nothing, just 250. But now if I map M, I get nothing. Because of the one failure, everything fails. So that's how the maybe monad works. As soon as you have a failure, the whole thing fails. So that would be one example. I mean, I could use this tree label thing.
Multiply by 2?
No, I meant like label several trees. So, I mean, we had this label SM. So I mean, we have our tree. Let's define a second tree, whatever. I don't know.
Single leaf?
A single leaf. Okay, I don't define it. I have that, and let's do one more that has like. And now I could, for example, map M function that takes a tree, I mean, just this label as M over this list of tree, just a leaf, Y, and this tree prime. So this is now state. So if I want the result, can do run state this thing, and I must give an initial state, so for example 1 again, so I start with 1, and now I get all three trees labeled but consistently. So I mean the first tree starts at 1, I get label 1, 2, 3, that is the first tree done, that's what we did there, but now it labels a single leaf with 4, and then the others with 5, 6, 7, 8, and the next label would be 9. So it's different to labeling them all starting at 1. It threads the state through the whole list in this case. So that's map M. And the underscore is a convention. I mean, it doesn't mean anything in Haskell. I mean, whether a name ends with an underscore. But the convention is that that means it has a unit result, or so you throw away the results. You are only interested in the effects. So for map-m, we saw, I mean, you have this effectful function in the list, and then you get an effectful computation of b's. And map-m underscore has the same input, I mean, the same two arguments, but it throws away this result list. So sometimes you are not interested in the result. For example, if you do, especially if the result is just unit. So for example, we could do map-m, if we do map-m put string line over hello world, then it will now print two lines, hello and world, so it will perform the effects, and it will collect the results in a list. And because put string line has a unit result, the result will be this list with 2 units, which is boring because that has no information for us. So in this case, we could use mapm underscore, and then it skips the result. So it just returns unit, and as we know, GHCI doesn't display a unit result. Okay. 4 is just a flipped version, because so it's the same as mapm, it's just with the arguments flipped. And that, I mean, often the function is more complicated than the list. And in this mapm version you have, I mean, for example, in this first example here with maybe, I mean, okay, this is maybe not a very good example, but I mean, the function that looks relatively awkward, and I need these two parentheses. So I turn, but sorry, I think that's not in scope, so I have to import that. Control monad for m underscore. So if I could equivalently write this with for m, so it's exactly the same when the list comes first. But now, because it's now the last one, I can make it nicer by using the dollar, and I don't need these parentheses. And it looks more like an imperative for loop. I mean, this almost looks like a for loop in JavaScript or something. So for, you iterate over a list, and you do stuff. So in this case, that would be that.
And the function can be super long.
Yes, and the function can be super long. So often if you have like a several lines function, then you use for instead of mapm, because with mapm you would have to, this like over several lines, you would have to put it in parentheses, and that looks somehow not as nice as this. And I mean, and the for m underscore again ignores the result. So I mean, if I want to print hello and world, I could also do for m underscore hello and world, and just put string line. And it would do that. So it's just a flipping. What else? So we have lift, map for sequence we saw. Forever is new. That does what you think it should do. So it repeats this MA forever. So it never stops, and therefore it has this MB result, but we will never see a B because it will forever repeat this computation. So that wouldn't work in maybe that would work in, but it wouldn't, and it's mostly useful in IO, I think.
Forever put string line?
Yeah, something like that. Or whatever, I could do forever, get line, put string, so this, for example, so as and Latino, Arena, and it would go forever. I mean, until I Control C out of it. Okay. Filter M. I mean, it's like filter for lists, but the filter can be can have a side effect. So it will go through all Or I could, of course, also like ask the user whether I should keep it or not, or whatever. I mean, do something.
Maybe write to the database if
Yeah.
if the user is something belongs to somewhere, you write to the database, else you don't, and then at the end you get the list of all the users that you modify, for example.
Right. Okay, that's filter. Almost there. Then when and unless we already saw, so it's only replicate left. There's this, I think I showed you yesterday, I mean replicate without an M. So the M, of course, is for monad. That's why, I mean, it's also a convention, a naming convention, that often there are functions, I mean, and it's broken as we see with forever, but in sequence, because there are no I mean, and when and unless, so because there are no versions for non-monads. But for map and filter, we have the pure versions, and then the M indicates that this is now the monadic version. So we have replicate without an M. It takes an integer and then just replicates a given element in a list. So I can a list of strings with 10 Haskell's. That's the normal replicate. And now with this M version, it can be monadic. So it can be a monadic thing, and then I replicate it a given number of times. So for example, again in IO, I could maybe 3 times do getLine. So now it asks me for a line, Haskell, asks me a second time for a line, and the third time for a line, and now it collects all my answers in the list. Haskell is great. So it replicates this given action 3 times and returns me the list of results. And again, the version with underscore throws away the results. So that would, in this case, be stupid, because I would have to type 3 words and then nothing happens. So there, for example, I could do and then it would write that 100 times on the screen. So,
why does replicate 10 when a string with like infinity? I just tried it and it was installed.
So replicate stops. I mean, I gave it 100, and after 100 times it stops.
I tried replicate 10 Haskell in a string.
Replicate 10 what? Did you try 10?
Any string, I guess.
Or without the M? Without the M?
With the M,
but I mean, it must be an IO action. I mean, the type of replicate M is, it must be in IOA in this case. So just the string doesn't make sense. I mean, that wouldn't.
Type check.
Yeah.
Oh yeah, now I see. That's probably one of these things. If I ask for the, it's a good question. I mean, let's see. Okay. That's like, if you wanted, of course, somehow the type checker has to figure out the monad. So, in my example, when I did it with put string line, then put string line has type string to IO unit. So the type checker knows that the monad is IO. So it does that in the IO monad. In your case, it's not clear. What monad should that be? But it must be a monadic computation. So, this thing, the string, which is a list of characters, must be in some monad, must be an expression in some monad. If you compare this, replicate M, with underscore and without, maybe with. So replicate M takes a number and then a monadic computation of A's. So we must have some monad, so this MA must be in a monad. But this MA is a list of characters, it's a string. So the monad is now not IO, it's list, so the list monad. And what does it mean to do this 10 times in the list monad? It means you have indeterministic computation that can have any of these characters as its results. And if you do that 10 times, then you have, I don't know how long that string is. That's 34 long. So we have an indeterministic computation with 34 possible results. And you do that 10 times. So we have 34 times 34, so 34 to the 10th power possible results. So it's actually, it won't loop forever, it's just a very long list. So, so this should be the length of the list. And that's probably too long to check, but if we do it shorter, I mean, if we maybe 5 times and just Haskell, then it indeed stops and it gives you all the possible ways to pick one of the characters. I mean, it gives you all the possible ways to pick 5 characters from the word Haskell.
A question on the same. Does it mean now the replicate picks a monad type that has already been defined prior? Because like
Yes. I mean, you must type check. I mean, if you do, I mean, it's the same, I mean, this has nothing to do with monads. If you do show, then whatever you write there, it must be, I mean, an instance of show, of the show class. Otherwise, it can't show it. And same if you use something that requires a monad instance, then it must be something where you have already defined monad instance.
I think the question is if you can specialize it before.
Yeah, I mean, you could give a type annotation if there's any doubt. I mean, same as for, I mean, I always get these annoying errors if I do something like this. Then Haskell always complains because it doesn't know, I mean, as I explained on last week, this 10 is not of type int, it's of any numeric type. And I always get this warning that it doesn't know which numeric type I mean, and GHI defaults to integer in that case. But I mean, I can help the type checker by saying, for example, it should be int. And then it's int. And same, you could also specify the monad you mean if there's ambiguity. But in this case, there was no ambiguity. It had to be list. That was an interesting question. That was funny effect. Right. So that's replicate, and that's it. I mean, of course, there are more, but this is just on the slides. And the cool thing is now you have these things for all our monads. I mean, for example, just for the state monad again, I mean, we have this label S, so we could now replicate, I mean, it doesn't make much sense, but we could replicate whatever 3 times. Label SM our tree. And state M. Starting with, I don't know, with 0, I'm sorry?
10.
With 10 for variety's sake. So now it would replicate, I mean, it would do, this is now in the state monad. So it would label the same tree 3 times. And originally it starts with 10. So first labeling, I mean, uses the labels 10, 11, 12. But then the next one 13, 14, 15. And the third time 16, 17, 18. And now the next one would be 19. So I mean, it works for any monad where it makes, it works for any monad. And for some it may make more sense than for others, but yeah. And I mean, for example, this sequence, I mean, no, that's a bad example. Never mind. I wanted to talk about this transaction, but that's like a combination of error and state because the bank is the state. So if we talk about transformers, we can revisit that. Okay, so that's that. Yeah, and here's an example how you could do this. Let me just check. So, I mean, we labeled our binary trees, but we, in the first exercise, we had this rows tree type. And yes, in the test, sorry, in the test. So let me just repeat this quickly. So data rows A is fork A and then a list of rows A's. Maybe deriving show. And let's define one. I don't know. So fork, let's take character again. Or we don't have to. Can take any type. Boolean. So let's say false, and now a list of rows trees. So let's say fork true empty list, fork false, fork true, fork true, and fork false. Like this?
The empty list.
Yeah, yes. Whatever, I mean, I just made one up, just something. So again, rows tree is, I mean, first of all, there are lots of tree types, of course. But I mean, in the one we always used as example, the data, the A's were in the leaves. And there are also versions where it's in the nodes, and this rows tree has the data in the nodes, and it can not only, those trees always had, either they were a leaf or they had exactly 2 children, and this rows tree can have arbitrarily many children, 0 to whatever. So I have one that has 3 children, and the first child has no, maybe we should draw this. Can you draw that? Anyway, just to have an example. I can write this, but it's of course not very enlightening if you show it like this. And what was the requirement? Okay, so labeling it. So let's call it label rows, which turns the rows of anything into rows of a label and an A. And again, as before, we want to start at 1. Let's say we start at the prefix at the top and then go from left to right. And again, we do that with the state monad. So we actually did. Sorry, can't see it. So we will use the state monad again. So let's call it label rows S for state, which takes a rows tree, and then is a computation in the state monad with an int state. Okay, and then I can use this by using this thing in the state monad, applying it to my T, doing eval state of this, and start at 1. And what's wrong there? Yeah, I must say the state, sorry, it's like this. Okay. And okay, 1 is too much. Okay, so I need to implement this. So there's only one case because there's only one constructor, fork. So I have some label at the top and then I have children. So what do? I must get the first label and label this A with it. So let's do that first. So I do get to get my current label. I increment the label. The new datum at the root is now this L paired with A. Okay, and now what next? Now I have the XS, so the children, so I must label all of them. And that's a perfect case for map M. So I can do xs prime is map M. So I map M my function label, or let's, for variety's sake, let's use 4M. So I loop over all the children. And what do I map there? Label rows S. Yeah, it doesn't matter. In this case, it really doesn't matter. Maybe I should stick to map M because it's so short. And now I can pure fork A prime Sx prime. And let's try it out. Label rows. Okay. I hope it works. No, it starts at the left. Yes.
Yes, but I think this one should be here actually.
Okay. Hang on. Let's just check. Otherwise, it's confusing. So first, no, yeah, true. Then there's complete with one, then false. Yes. There's one with false still on the second level.
Here?
Yes, next to those two. On the right, there is one with false.
Then this is 4.
6. Right, and I think that's exactly what I got now. So it always starts at the top, and then goes from left to right. But it first goes all the way down.
Here, then.
I mean, yeah, I mean first the 1, then it does the children one by one. So it starts with the leftmost one, there's the 2, then it goes to the middle one, again starts with the 3, and then goes to all the children, and then goes to the last sibling there with the 6. And that is now, I mean, using this map M. So the point of this example is this map M, that this is now useful because I have the list of children, so I can just with map M label them one by one, and then I get this nice thing. The example itself is not important, of course. And this, I think, yeah, okay, applicative we already have, so I told you that, so this all...
The old in a new way, just in case they...
Yes, but there's before there's this. There is this slide. So that's like brain teasers to recognize what, I mean, it's mostly the list monad, I think. And I mean, we actually now, because of this question, we already saw that. So what was, sorry, replicate M2, 1, 2, 3. Let's try this. 2, 3. So, I mean, we saw this example already because you asked. So in the case of the list monad, it will basically, because replicate 2, so this will now be all possible ways to twice take from 1, 2, or 3. So it's all possible pairs from the list 1, 2, 3. So 1, 1, 1, 2, 1, 3, 2, 1, 2, 1, 2, 2, 2, 3, and so on. Okay, what's the next? Map M. Okay. Map M return 1, 2, 3. Let's see.
Nothing.
That should do nothing, right?
Yeah. We spoiled it.
Right. I mean, mapping return doesn't do anything. So in the monadic world, return or pure is like the identity. So that is the same as if I would map the identity over a list, which also wouldn't do anything. Okay, this is interesting again, I think. So let me write it. So sequence, if we recall the slide, for an arbitrary monad, it takes a list of monadic computations and turns it into a monadic computation of lists. Yeah, so it collects all the possible results of each computation and lists all of them. So let's see. in the monad. And now this is like really a brain teaser or something. I mean, this is a bit evil. So the point is that, I mean, there are two lists now, but I mean, sequence takes a list of monadic computations. So the outer list is the one that comes from sequence. But the inner lists are now, that tells us that the monad again is list. So we have a list of indeterministic computations. And now it will turn that into an indeterministic computation of elements. So it will be, so it's basically it gives us the list of all possible ways to pick one from each of the lists. So I can pick 1 or 2, I can pick 3 or 4, and I can pick 5 or 6. And this is basically all the possibilities I have there. So the list monad is great for like combinatorial stuff. I mean, it's already.
List of just, maybe? A list of just?
Yes, if I do a list of, that I have done it before with the lookup, that was an example. There are great examples, fun examples for the list monad, but I mean, today is too late tonight, but we can maybe do that tomorrow or so. Right, what next? This is now, I think, the lookup from the prelude, right?
Yes.
So I think this is basically exactly the same that I did before for the account lookup. So if one of these lookup fails, then you get, I mean, if all of them succeed, you get a just and list of the results. And if one of them fails, you get a nothing, even if the others would work. I mean, that we already saw that example. And maybe let's do this last one. No idea what that does. Let's see whether we can figure it out. So evil state, replicate 5. Oh, we haven't seen modify. I should rectify this. So modify is also from this control monad state. So it takes a function from S to S, and then is a stateful computation without an interesting result. And what it does is it asks for the state and then puts F applied to the old. So it modifies the state by the given function. And that probably will, because this is defined in control monad state, so let me just hide that as well. Okay, now I can continue. Now I can't because I have to reload.
But I think you have, I think you have the other one already.
Okay. Okay, let's type that again. Evil state. Replicate m underscore 5. So modify plus 2. And then get. That's the computation and this whole thing starting with state 0. So can we figure out what that will do? So it will, I mean, in the end, it will evaluate it for an initial state of 0. And it will do 5 times the same thing. It will modify the current state by incrementing it twice. And then do a get. So it will then afterwards look at the state. So that means we start at 0. The first time we do it, the state becomes 2. And the result, because get looks at the state, is 2. The second time we do it, state is 4 and we get 4. So we should get 10. 10 should be the answer. Fuck. Yeah, because I must say that it's integers. That's again this annoying thing. Okay, but in the end I don't get a result because I throw it away, because I replicate underscore. But if I didn't throw it away, maybe we should change that slide. Okay, then I get all the results. So after the first, the state is 2, then 4, then 6, then 8, then 10. Yes. Anyway. Okay, and I think this now we already did. So this is on the slides how you can use applicative to make that look nicer. And that all of this. Okay, and this is just right. Why functor T? T is a very bad.
It was called like that. The name of the type.
Oh, okay. Right. Yeah, it's good. Sorry. Yes, all good. Okay, I mentioned this, that there's like, historically this is shifting. So this was the old way. Monad had return and bind, and then you would implement applicative in terms of and functor in terms of that. So functor as now, as we saw, lift M, but you would define pure as return and the star thing as AP. And now the new way is, as I showed you, so monad you only have to define bind, but now in applicative you define pure. And now the return in monad you don't have to write anything, that has a default implementation, but the star is still app and the fnode is still lift M. The difference is now that, like until recent GHG versions, basically all you had to do was in the monad class, but there then return and bind. And now that has changed. So now only the bind is in the monad class and the pure you implement in the applicative. So it's, but I mean, logically you have to write the same code. It's just arranged differently. Okay. We saw that. Right, and this is just the last slide of this lecture. So, but in principle, I've seen and said all of that. So monad is very useful for lots of types, and I mean everybody needs to find his own way to think about monads. But I think of them as effectful computations, where the effect is like we can choose the effect. There's the built-in one with I/O for real-world side effects, but we can pick other effects like exceptions or state or and so on, or indeterminism. And then they have a lot in common. So they all have this pure and the bind and the applicative syntax, this one. So we can, many things like we saw on this slide, we have available for all monads. So it's very useful to have this abstraction, because then these things we can always use whenever we are in a monad, and do notation we can always use. But they also have like their special flavor, each of them. Like I/O, you can do real world side effects, and in either you can throw an error, and in state you have this get and put and so on. So to understand the monad, we basically need to understand how bind works and pure works, and then what like special effects does it have. Like in the state monad, it has the special effect that you can read the state and write the state. And in either monad has a special effect that you can throw exceptions and also catch them, even though we didn't see that. And you must understand how the bind works. So in the case of the state monad, the state gets threaded through. So each computation has access to the state and can update it, and then the next one gets the updated state. And for example, the point of either or maybe is that as soon as there is an exception, it stops. And the computation just stops. Right, and we will see in a later lesson how you can combine these effects to have more effects or more complex effects. So that's that, and I just need 10 minutes or so to complete yesterday's lecture and show you how you can get code coverage. But are there any questions to monads at the moment? Don't worry, I mean, this is, as I said in the beginning, normally the biggest stumbling block in learning Haskell is understanding monads. But I hope that I gave you enough examples to at least. Okay, if there's no question, then let me switch to yesterday's lecture, because I still wanted to show you how to do a proper test suite and how to do code coverage. Just I didn't have to do that, sorry, but it doesn't matter. I always forget where I am. Okay, close. goes. So let's go back to yesterday's code. So now I added a test suite again. So in the, first of all, here in the Cabal project, so I mean what I showed you in the beginning of yesterday's lecture, and then I removed it because it didn't work properly. So now I added this test suite again using Cabal init, so I didn't have to write this by hand. And now I'm using HSpec, so that's like a unit test or framework, or also a test running framework, which in particular can execute quick check tests. And I have this new, so this is now the executable of the test, which Cabal test will run. And one of the reasons I wanted to do this at the end of this lecture and not at the beginning is that HSpec uses so-called specs, and there we see a do. So spec is also a monad, or spec, actually spec is a synonym for spec with something, and spec with is a monad. And I mean, it doesn't matter. I mean, they basically just use it to structure tests. So using this do notation, they can nicely have like hierarchical tests. So you can like order your tests somehow by groups and functionality and so on, using this describe. So for example here, so this test is, I mean, Haskell, and then in the simplest case you can just have a Boolean, so no quick checks. So with it you can have individual tests, so whatever, and then you have a condition. And now if that condition, and I can execute this stuff, so if I now made that wrong, and now do Cabal Cabal test, then so it runs it, and there's an X, so that means it's wrong. These two tests pass, and then it gives me the failures and says exactly where the failure is, and this label again thing, this description. And so let me fix that again. So if I fix it, then it just says passed, but there are command line arguments, so you can make it that even if everything passes, you can still see all the tests. So there are like configurations for HSpec. And but the interesting part is now for quick check, there is this prop thing, so prop and label for the test, and then something like that we yesterday used, quick check sort preserves length, or sort ensures is sorted. And with this prop, that is basically the link between HSpec and quick check, so that you can run your quick check test in an HSpec specification. And as we saw, and I mean, maybe I should make something fail. So if I go back to the implementation, or maybe there was this drop twice, which was wrong, right? So maybe I should test that, or can.
Drop twice and short.
Yes. Drop. Prop should do the right thing, doesn't matter. And I can just do drop twice now, I think. I mean, that is already a prop. And now that should fail, because we saw that that doesn't hold this property for drop. Right, and yes. So again, I mean, as before, so arithmetic checked, sort checked, drop has this X, and we see the failures, and we see this counter example that comes from quick check that we saw yesterday. So for which values of the variables, of the arguments, it doesn't hold. Yes, so maybe I should fix the test, I don't know, or remove it again. Maybe remove it again. Okay, that's that. And the last thing I want, or second to last thing I wanted to show you is the program coverage. So now that should work. And you can just say, I mean, minus after Cabal test, enable coverage. And hopefully this works now. Okay, now there's a slight technical problem. So it writes this HTML file here, but I think, I can't, I could look at it in the editor, but that's of course not very helpful. I want to look at it in the browser. But because I'm working in the container, there is no browser installed. So let me do the same thing from my local machine. Cabal test, enable coverage. Okay, and what the fuck? Sorry, that's always if you switch between the container and your local machine, then sometimes it's, so I just shown -r sudo do it like, but now I could, so it's all good. Right, so now it worked. So that's just a Docker thing. And now it wrote it to here. And now I should be able to open that in my browser. Okay. So basically you get a report for all your modules under test. In this case, that was only one module yesterday. Otherwise, you would get a line for each of one. And you, get some statistics here, how much is covered. But the nice thing is actually if you click on this link, because then there's the source code of your module, and then it's colored. So yellow means it's not covered by test. Green means it's a condition that's always true. So that could be a hint that some branch is unnecessary because something is always true. But here we, for example, get it for otherwise, which of course, because otherwise is a synonym for true. So of course it's always true. So that, and red means always false, but we basically don't have red. So the interesting part is the yellow. So yellow is stuff that is not covered by our tests. But the white stuff is covered. So in particular, like the sort function is completely covered and the insert is completely covered. So in that regard, our tests are good. At least they execute all our code. And there's one annoying thing. If you just do it like what I just told you, you will get an error message because there's a new feature in Haskell in the newest version, some whatever internal module, internal packages or libraries it's called, which conflicts with this test coverage. So it doesn't work with some libraries, and that resulted in error on this. And because of that, I added this file here to my. So it's like lying next to. It's on the same level as the Cabal file. So every Haskell project, in addition to a Cabal file, there can also be a cabal.project file, and there you can do all sorts of stuff like specify which GHG version you want, and you can like change dependencies. So even if some package says it needs this specific version, you can change that. And one of the things you can do is you can tell it that you want to switch off coverage for certain packages. And this autoparsec, that no idea how that gets there. It's probably used by HSpec or something, and that doesn't work with coverage, and therefore I had to add this to explicitly switch this off. So that's a bit annoying. That wasn't needed like 1 year ago, but it is what it is. Right. So that's
really cool, the website. Like,
yes. You mean this coverage thing?
coverage,
Yeah, that looks nice, doesn't it? Yes. Okay, and the last thing I wanted to maybe do is look at the code from yesterday with this binary tree, because now we know that that gen is also a monad, and I was still not happy with this gen tree thing, with this here, because it's still, it's somehow not correct. What we really want to do is, the idea was generate a random tree with at most the given number of leaves. Or actually, let me change that. let's, with the given number of leaves. Okay, so if it's less than 1, okay, we do a leaf. And otherwise, so right, I mean, so now so the n is not 1, so we have at least 2, so we need a node. So we need to recursively generate a left son or daughter, whatever, left child and a right child. And we must recursively call that, so we must somehow say, I mean, how many leaves should the left child have and how many leaves should the right child have. And we can pick that randomly. So, and of course we must be careful that, right. So let's just, so now that we know it's a monad, we can do this. And let's say, for example, n left. Sorry. So elements picked a random element from a list. So which choices do we have? I mean, at least 1. And at most n minus 1, because we must leave 1 for the right child. So why does it complain? Oh, yeah, okay. Right, and then we can just say, okay, and then the right one must get the other leaves. And now, for example, we can use applicative and just say node gen tree nl, gen tree and right. So this is very nice, and this is much better than before. So this is now a function that generates, I mean, a random tree with a precisely given number of elements. So we can actually check that. So for example, I could say with sample. So let me just cabal REPL. Okay, so let's say sample gen tree, I don't know, 5, gen, I don't know, tree int. And now this should all be trees. Maybe 5 was too big, that's too hard to see. Let's say 3. So this should now all be random trees, but they should all have exactly 3 leaves. And that's looking good, right? And now we can, and it should be all possible ways basically. So now we can generate every possible tree. That's the point. And now for the arbitrary, so I have to slightly change this because I don't want to, for size n, generate exactly n plus 1. Maybe I want, so I can use do notation here as well. And I can pick how many I want. So I want between at least 1 and at most, let's say, n plus 1. And then gen tree m, for example. And now, if I do arbitrary here, it should hopefully, yes, so it starts with very simple trees that just have a leaf, and then it slowly increases the number of leaves. But in between, there should also every now and again be shorter again. I think that works now. Yes, so this is just another example. So now we have 2 more examples of monads. Didn't I save? Oh, no, that's another problem. So we have this spec stuff for the unit test, and we have this gen. And then because of what you learned today with do notation and applicative syntax and so on, so this is all, I mean, once you understand that, you can use it in so many different situations, like writing quick check generators. So that's also another advantage of this abstraction, the monad abstraction, that once you have understood it, it's applicable for so many cases. Okay, so that's basically it for today. Any questions? Okay. Then, now you know monads.
Okay. Amazing. Thank you, everyone. remember that the weekly, it's already up there in the outline. So you can work with it with at most 4 people. Groups can be teammates can be at most 4. Or can be 1 if you're a lone wolf. Yes.
I don't know if it's just me, but if you consider extending the timeline, the deadline for the assignment, I think at this point it's a lot to take in and do the assignments.
This week we have only one personal and only one group assignment, both till like Sunday night. But do you think we could like, or maybe let's see. No, because if I say less than X amount of people, no one will push. It will work locally. Okay, what about like half more week? Because like next week there's another weekly assignment and it will like pile up.
But I mean,
later.
we did say that we want to slow down a bit once we are not here anymore.
Yes.
So I think it's okay to do it until Wednesday or something, the group assignment.
Okay, so...
I mean, we don't have to immediately, I mean, we can still see, but whether we do the next lecture on Monday immediately or maybe then we give them 2 days or so to work on the assignments.
Okay.
I mean, we just want to use the time we are here as best as well as possible.
Yes.
And of course, it would also be good if you work on the assignments while we are here, because then we are still in a better position to answer questions if you have any.
Yes. So likely we are going to slow down in the next weeks to make sure everyone can catch up and maybe stretch a bit the course instead of 2 months, 3, 4, depending on. Because like there's no use if we can just rush everyone and like for some reason like other things you have to do, you have to work, etc. You cannot keep up. So yeah, we're going to stretch out the course, so you will have more time. Next week's maybe just 3 lectures per week, and the other days you can work with us. Maybe we can be online or just able to answer questions for some amount of hours. So yeah, I'm going to spend all the ones of the first weeks are done, but it's okay. You can still do the other ones. Don't worry. So until next Wednesday, and maybe likely Tuesday there won't be any lessons, so we can like work with you.
I mean, we still have to discuss the details, but I mean, the original plan was to have in the next weeks to have 3 lectures, and now we said we could even lower that to 2 or so and stretch the course. But I mean, whatever. But yeah, I think that makes sense to.
It's good.
Yeah.
If for some reason like everybody struggles with that specific, we can extend it more to give you more time to work it. But yeah, like I said before, I don't want like everyone to work then like to accumulate weekly stuff. Yes.
Yes.
So I think
Some
that's
point.
it.
Yeah.
Okay.